Our next speaker is Terry, and his talk is entitled Orchestrating Granular Access for Sensitive Omics Data, the SAFES Architecture within NCHC's Trusted Cloud Platform.
Okay, thank the introduction. Hola, everyone. I know I'm the only thing standing between you and lunch. As the last speaker of this morning session, my name is Terry. I'm from the National Center for Hypermesh Computing, National Institute of Applied Research in Taiwan. Today, I'm going to introduce a system we built within our trusted cloud platform. It's called SAFES. And I will be talking about how we use it to manage and orchestrate a granular access control for highly sensitive omics data. Okay, let's dive in. First, let me give you a quick background of about NCHC. We provide supercomputing. We provide supercomputing power and the research network service to academia and the government agency in Taiwan. In fact, we are the only nation's large-scale shared computing and networks facilities. In recent years, we have expanded our focus well beyond traditional HPC. We are now heavily involved in several fields, but the most important for today's talk, we have been focusing a lot on building such a research environment. Under our national mandate, NCHC operates on 4 major mission pillars, which you can see here: AI, HPC, big data, and network infrastructure. To break it down quickly, for AI and HPC, we deploy long-term large-scale computing power and provide a highly reliable environment for national R&D initiatives. For network infrastructure, we construct Taiwan national broadband backbone to strengthen network resilience. But the most relative pillar for today is big data. Our goal here is to establish multi-domain cloud platform that deliver a high-trusted environment, especially designed for handling sensitive data. Ultimately, our vision is to create a secure and integrated cloud big data computing ecosystem. To build this ecosystem, we have set 3 major development goals. First, providing national level data service and delivering digital governance service, and enable cross-domain integrated application services. To achieve these goals, NCHC has established a secure cloud data analytics infrastructure, which we call Trusted Cloud Platform. So, what exactly does the Trusted Cloud Platform offers? It provides a highly secure and reliable cloud environment built on the core services. First, the secure and the data protection. We provide your data through comprehensive cybersecurity control and end-to-end encryptions. The second, we offer elastic computing, which includes standard virtual machine as well as Kubernetes container service to give researchers maximum flexibilities. Last, to make everything user-friendly, the platform featured an AI smart assistant. This assistant guides users to set up and troubleshooting, lowering the technical barrier to make it much easier for everyone to get started. Okay, now let's look at the actual architecture of the Trusted Cloud Platform. As you can see, the platform is strictly divided into two areas: the sensitive zone on the left and the general zone on the right. The general zone on the right acts as a typical public cloud, offering standard VMs, Kubernetes, and storage. On the left, the sensitive zone provides a dedicated environment where research can safely process sensitive data. We have made it so that virtual machine and the container image built in the general zone can be transferred one way into sensitive zone, and any data sharing between them goes strictly through our data exchange service. Currently, this design works great. If a researcher brings their own sensitive data, share it with collaborators within the secure zone, and ensure it cannot be easily leaked. However, here is a catch. This setup may not fully meet all the complex usage scenario or the incredible stringent compliance and secure requirement that comes with sensitive big data service. And that brings us to a challenge we need to solve. Let me give a real-world example of why our architecture needs to evolve. Let's look at our enduring partnership with Taiwan Biobank. Together, we built a comprehensive data release system. Currently, the Taiwan Biobank hosts a large data set, around 2,000 whole genome sequencing samples, including alignment and variant coding data, alongside roughly 200,000 genome typing profiles. In total, the massive repository exceeds 1.3 petabytes of secure storage. For researchers in Taiwan to use this data, they go through a 9-step workflow shown on the top right. They submit an application, pass reviews, and once approved, they are granted access to work with this genomic data directly on NCHC's HPC environment. In addition to the Taiwan Biobank, NCHC collaborates with Academia Silicon, National Taiwan University, and some major medical centers on the Taiwan Cancer Moonshot Project. This landmarking initiative has led the incredible scientific breakthrough about the non-smoking lung cancer, including several high-impact factor journal papers. To support this world-class research, NCHC helped build the official Taiwan Cancer Proteomics knowledge base. Much like the Taiwan Biobank model, researchers can apply to analyze this multi-omics data directly within NCHC's HPC infrastructure. And let's look how we used to handle this in our traditional HPC storage environment. In the past, before collaborating with NCHC, the Taiwan Biobank used to release data directly to researchers by giving them the actual files. They give the files stored in the NAS and give the NAS. But the data scale explode. They shift to an HPC analysis model. When a researcher is approved, they never get the whole data set. They only get access to a specific subset tailored to their project. To manage this granular authorization without wasting precious space, we adopt a zero-copy approach. We combine hard links and the file ACLs to dynamically group different files and folders into an approved dataset to each user. However, this method has a major physical limitation. Hard links only work if everything resides on a single storage volume. They cannot cross different storage systems or hardware device. Furthermore, global trends in biomedical research on demand strict data loss prevention, meaning a raw data should never be downloaded to the endpoint. It must stay in a secure, closed environment. While moving to our trusted cloud platform seems like the perfect answer. It raises a critical question. How do we orchestrate this level of granular access control inside a cloud platform? To meet the strict compliance need for the sensitive data in the cloud, we designed the sensitive data access and the file exchange system. To make this system highly effective and secure, we decided to decouple this architecture into two major components. The first one is SAFES, which handles all the complexity of authorization logic and the data access control. The second one is SafeGate, which is responsible for managing the mechanisms of the actual data exchange between zones. The diagram may not look similar the TCP architecture I showed, but looks at the bottom left, we successfully implement the SafeCore service and heavily enhance our data exchange capability with SafeGate import and export. I know some of you might thinking about right now. We are about half through my presentation, and I haven't mentioned about IRAS. Don't worry, you are in the right room, and the wait is over. Right here is where IRAS officially entered the picture. We integrate IRAS directly into the SAFES architecture. Let's look at how it works. A few years ago, when we trying to solve the data access control challenge in the cloud, we spent a lot of time evaluate various commercial solutions. During a technical discussion, an engineer from Quanta Computer, a well-known Taiwanese server manufacturer, recommended IRAS to me. After diving into it, I realized it was the perfect fit to our use case. IRAS bring us 4 core competencies to the table: data virtualization, data discovery, workflow automation, and secure collaboration. Today, let's focus on the first one, data virtualization. For a user's view, files are presented as a data object organized into collections, completely decoupled from the physical hardware. User access data exclusively through an IRAS client with complete local transparency. They don't need to know where the data physical resides. Because of this powerful feature, I can achieve the exact same goal as our traditional HPC hard disks. I can simply register and combine any existing physical files across NCHC storage into a ICAD catalog without moving or copying a single byte of data. This completely overcomes the physical boundary of a single storage volume. Moving to another core competency, let's talk about secure collaboration. As I mentioned, when dealing with massive data set on a terabyte scale, copying files between different physical locations is simply impractical. We need a way to share data safely across different projects and work group without any physical data duplication. This is where IRAS access control model comes in. Its permission are beautiful model after standard Unix file system. By utilizing this, we can manage and enforce all data permission directly within the ICAD catalog level. It allows us to assign specific data set privileges to different research groups smoothly and securely. With SafeCore, we can now achieve an architecture that functions very similar to our previous HPC hard disk environment. In a cloud platform multi-tenant architecture, we need to cater a different projects simultaneously. On the left, we have our raw data in sensitive zone storage. In the middle, the safe core leverage IRAS to perform registration. Grouping those massive files into tailored data subset without copying them. Finally, on the right, a data user within different projects can spin up within their virtual machine inside TCP's sensitive zone. By using the IRAS client, the VMs can securely mount their specific data set with the executive permission assigned to them. This provides an isolated, compliant, and zero-copy data environment for every single tenant. Now let's walk through the actual workflow inside SafeCore. This diagram shows how their distinct roles interact with our system. The storage admin, the system admin, and the end user. First, let's start at the bottom right with the storage admin. Their main job is to ensure that the sensitive data sit on storage hardware accessible by IRAS server and the system daemons. They handle the initial data transfer over a secure encrypted channel via the NCHC's intranet. Once the data is in place, the system admin takes over from the top left. Operating strictly through a secure BDI, they log into the TCP portal UI to import the files. During this import process, the system automatically calculates the checksum of each file and logs into our PostgreSQL database for integrity checking. After that, following instruction for the data controller, the admin assigns access privileges to specific project group. Our service daemon then automatically registers these files into IRAS, tying the dataset and the groups together. Finally, look at the end user on the top right. To access the data, they must also connect via the VDI into the sensitive zone and launch their VM. After passing the authentication through our LDAP server, the VM automatically mounts the approved dataset using IRAS FS for secure read-only analysis. Now let's take a closer look at the SafeGate orchestrating data import and export, maintain the maximum security. As you can see from the legend, the purple and the orange arrows map out the inbound path, while the gray and the green arrow shows the outbound path. Let's start with the data import process. User first log into the TCP portal UI from the general zone and upload their files. Our service daemon instantly moves this data to a dedicated temporal storage to perform restrict file security check. Once it passed the security scan, the daemon compresses the data, transfer it directly into the sensitive zone storage, and automatically notifies the user. From there, the researcher can safely connect via VDI, log into the sensitive zone, and download the data onto the VM for an analysis. But what happens when the researcher wants to take their results home? That brings us to the data export process. The user triggered an export request from the secure portal. Before anything moves, the service daemon queries our database to compare the data hash, the checksums, ensure that no raw sensitive data are leaking out. After checksum verification, the data is staged in the temporal storage, and a notification is sent to our data admin. The admin connects the VDI and to review the data and make the final decision. Once approved, the data is pushed out to the general zone storage, allowing the user to retrieve it safely. And that concludes our complete data authorization and protection workflow under the SAFE architecture. Yeah. Due to the time constraint, I skip this one. Okay. Finally, it's the last page. The conclusion. By combining TCP with SAFES, we could say that our infrastructure fully meets the 5 SAFE framework required for a trusted research environment. The first, safe data, meaning our storage tree data to protect any confidential concerns. Second, the safe project, the data owner approve access based on the research criteria. Third, the safe people, ensuring researchers are authorized and trained to use the data safely. Fourth, a safe setting, which is achieved our dual zone TCP network environment that functions just like secure lab to prevent the unauthorized use. The fifth, a safe output, which is heavily managed by our SafeGate hash verification and admin approval process to ensure non-disclosure data release. From the inbound and outbound workflow I shared earlier, it is clear that our sensitive data service strictly complied with these international standards. That concludes my presentation. Thank you so much for your time. I would like to open the floor for any question you may have. Thank you.
All right. You got a question right here? Yes.
Thank you very much for a very interesting talk. I'm Martin from IT4I. We are also HPC Center, and we are also trying to solve a very similar problem with our platform. But I have a question about the hard links. Yeah. Because what bothers me a little bit in the design is in case I need massively parallel access to the files. Do the files reside on some all-flash storage, or is it a combination, or is it just mechanical hard drives? Yeah. If the storage is performance optimized. Yeah. So my question is if the files which the hard links are pointing to, on which storage they are actually located, what type of storage is it? Is it HDDs or flash?
It's in our GPFS.
GPFS, and this is okay. And this is backed by flash drives or tiered or?
It's hard drive.
Hard drives. Yeah. So it's capacity optimized.
Yeah.
Yeah. Okay. Yeah. Because in our solution, and we will have a talk, and we are trying to focus on staging instead. Yeah. To improve the performance. But this is just a different way how to do it. Yeah. But yeah. Thank you very much.
All right.
Yeah.
We have another question. All right. Thank you.
Thank you.